And good morning, Vancouver. This session is titled New Developments in Materialx and OSL. And I'm Jonathan Stone from the Lucasfilm Advanced Development Group. Let's give this a try. Let's advance to the next slide. Thanks so much.
Oh, I don't have to do it? Okay.
Let's see, so we have a great lineup of sessions planned for today. I'm just going to give a quick overview, and then I'll hand it over to the actual presenters. We'll be starting with Moeen Syed, who will be talking about the Open Chess Set, which is a new open source asset based on USD and Materialx. That'll be a visual theme for a lot of the other talks that we'll have today, and likely some other talks at SIGGRAPH this year. Then we'll have Nicolas, Guiard, Emma Holthouser, Gunnarsson, Brian Savery, Bernard Kwok, Pablo Delgado, Lutz, Kettner, talking about improvements to Materialx as a code base and integrations of Materialx into new packages. Then finally, we'll have Adrian Eruvel and Chris Culla talking about a new collaboration between Materialx and OSL that we're really excited about, implementing the Materialx closures in the open shading language. And then finally, we'll have Larry Gritz giving an update on new work directly in open shading language for this year. Hopefully all the room reverb is fixed. I'm going to turn back on my sound. And without further ado, I will hand it over to Moeen Syed.
Thanks, Jonathan. I hope everyone can hear me. Okay, awesome. Welcome. This is a beautiful game, the Open Chess Set. So I am Moeen Syed. I'm a visual effects artist and co-founder of 9between. This presentation is for SideFX. Next, please. All right, so this is just going to be a brief overview of the Open Chess Set and how it came to be and kind of what it is at the moment. Next slide, please. So it started with a beautiful game, which was a Karma and Solaris learning material that we created for SideFX. So as part of that, we created a USD compliant set of assets that had all sorts of textures and 3D models attached to it, and that was created by Mujtaba Syed. And we used it to explore the various workflows inside of Solaris, as well as how to work with the various shader options that you do have. One of the parts of that was actually working with Materialx shaders. So as opposed to just using the standard Vex-based shaders that you would inside of Houdini, we worked with some Materialx stuff, and that became part of the learning material. And we rendered that in both Karma CPU and XPU. Next slide, please. Yeah, so the Open Chess Set. Those assets that we created for the learning materials were available publicly. And so the next logical step was to just open source the entire set and turn it into a open source Materialx asset. And so that's exactly what was done. And thanks to Chris Rydalk, he converted the materials, extracted the geometry from the original files, and with Chris and Mark Elland, they managed the process of contributing this to the Materialx repository. Pablo Delgado created a compiled USD asset, and then thanks to Jonathan Stone, he fixed any issues and completed the conversion to MTLX and GLTF. Next slide, please. So there are a couple of benefits to having this as an open source asset. Firstly, it acts as a shared consistent testing asset. So you can develop comparisons between various render engines, all using the same set of Materialx assets. Additionally, because of the way that the asset was created, and you will see this shortly, there were a lot of shading features integrated into it, such as transmission, metallics, and we had all sorts of things all set up within a single scene. And so from the side of SideFX, there are some benefits to their clientele. Obviously, it encourages the experimentation of third-party renderers within the Solaris context. And it allows Houdini users some flexibility and exploration. They don't have to create a set of assets that have Materialx. You can just get it. It's open source, and you can play around with it inside of Houdini. So due to the conformity to open standards, it is accessible for personal and professional research and development. So this does open up some avenues for further developments. Additionally, it acts as a unified anchor point for discussion. And again, this goes back to acting as a shared consistent testing asset, but basically it now provides an anchor point for discussion and exchange, acting like a benchmark between renderers. So it's very easy to draw comparisons between renderers using the same materials and the same shaders. Next, please. So here we have one of the renders that was done in Karma XPU. So all of the ones that you'll be seeing here were done with Karma XPU. These were taken directly from the open source chess set and brought in, just some lights were added, very basic environment. And this is what you end up with. So as you can see, we have transmission, metallics, normal maps, all sorts of roughness maps, all of the good stuff that you'd expect. And this is all Materialx. Next, please. So you can see it's a bit more of an zoomed out sort of shot over here. Again, just the same thing, giving you an idea of the variety of materials. Next, please. Over here, you can see that we do also have some of the other shading functions, such as subsurface scattering, as you can see on the king piece. And so, yeah, next slide. Finally, just another render, just to kind of show it off. So, yeah. And that will bring us on to kind of how this actually works inside of Houdini. So with this video, I'm just going to play it and take you through this very briefly. So the way that this works generally in Houdini at the moment is in the Solaris context, you'll bring in a USD asset. I'm not sure if the video is playing on your side. Okay, brilliant. So yeah, you bring in a USD asset, and if it doesn't have materials on it, you'll go into a sort of material library, create your shaders. There's a vex-based shader and a Materialx-based shader, lights, cameras, as you would. And yeah, you know, these are two side-by-side comparisons of a vex-based shader, so the Houdini native shading, versus a Materialx shaded piece. And it looks nearly identical. And this is rendered with Karma CPU. And at a sort of higher level, what this actually looks like inside of Houdini for anyone who's interested, we'll be looking at in the next slide, please. Right, so in terms of a VOP context, how this is built, you have the standard surface shader, and this excludes displacement. So you bring in a Materialx displacement node as well if you need. And this is a common workflow inside of Houdini where you would take the two and then collect them. Now, generally, you would use just a collect node, but now there is also the option for the Materialx surface material, and that acts as a collect node as well. But I would suggest obviously using the Materialx surface material because that is built with this functionality in mind. You can still bring in all sorts of attributes with global parameters and bind nodes. You can also use the Materialx image node to bring in particular texture maps. As you can see, you can bring in all sorts of material maps, all sorts of texture maps like that. Again, you would have the usual access to things like a normal map to convert to the correct space. You'd also have you'd also bring in Materialx images, put it into your displacement, and have access to things like remapping. So if you need to remap a particular displacement, you can go from a particular range to say -0.5 to 0.5, if that's necessary. Additionally, also, you'll have access to all of the math functionality that you may look for. And so the workflow now with Materialx is fairly seamless if you're coming from a sort of vex shading background. So yeah, that's it. That's just a few closing thoughts. Onto the next slide, please. So the open chess set has been proposed for the for inclusion in the digital production examples library, and that will be presented in their segment later today. So if you are interested, please do check that out. Just a thanks to a few people. Thanks to Chris Rydalk, Mark Ellent, Pablo Delgado for their efforts on the open chess set, and a special thanks to Rafal Jaroskovic and Jonathan Stone for their assistance with information for this presentation. So I hope you enjoy the rest of the presentations today. Thank you for listening. Bye.
So hi, hear me? I'm Nicolas Guiard at Isotropix. Today I'm going to talk about Materialx inquiries. Next slide, please. So, sorry. In case you didn't know, Isotropix is developing query, but really this is utilized in layout, scene assembly, lookdevx, and rendering. Our software is used a lot in the effects and animation by different types of customers, ranging from down to freelancers working on many feature films, TV shows, and commercial. Next, please. Queries also comes bundled with its production-proven renderer that has been massively used to render over 1,000 shots on the recently awarded Dune. Kudos again to Dineg for the amazing work on the movie. Next, please. So, back to Materialx. Why do we love Materialx and why do we think it's the next big thing? Well, yeah, we software vendors suck. Why? Because no one has been able to offer users the ultimate solution. Everyone is using a combination of multiple software to create images, and it's quite common to use multiple renderers on single shots. These software are obviously very different, otherwise that wouldn't be fun, and they run on a large variety of technologies around CPU, GPU, hybrid CPU, GPU hardware such as the Apple Silicon. And of course, there are two different categories of renderers, since there are real-time and offline rendering solutions, which have all their pros, cons, and limitations. So, what do users that are forced to use very different software altogether want? A simple, hassle-free way to efficiently exchange their work from an application to another. Next, please. Fortunately, there have been some amazing production-proven solutions from the VFX animation community to alleviate this issue. Alamig and USD to exchange scenes data between packages, and OpenVDB for volumes. But exchanging looks is very tricky, and even if most looks today are driven by PBR-based maps, users still need to rebuild shaders and optimize them for each rendering engine platform. And obviously, this is hard because there are tons of real-time and offline solutions having each proprietary look descriptions. Next, please. And when I mean tons, well, it's literally a jungle out there. So yeah, the promise of Materialx is really pivotal. Now let's see under the hood of queries. The support of Materialx has been introduced in Queries 5.5, which is available in early access since December 2021. Materialx looks are exclusively rendered with NG, our next-gen OSL-based CPU-GPU renderer, which is going to replace our classic renderer. In queries, Materialx documents can be accessed in Python or in C++. This is very useful when writing pipeline tools or for third-party renderers integrated in queries. Next, please. In Queries 5.5, users can directly manipulate a graph of Materialx nodes. The updated Materialx document is then passed to Xgen, which generates the OSL code. At this stage, we are also injecting custom OSL code to call ng's proprietary closures and functions when needed. That aspect is another great thing about Materialx, since it gives us plenty of hooks to controls, and controls to perfectly integrate it to our renderer. Finally, everything is compiled for the CPU or GPU backend right before rendering. Okay, let's now see Materialx in action in queries. Next, please. In queries, users have access to all Materialx nodes to create their looks. Once the look is created, they can export it to an MTLX document. Next, please. Obviously, it is possible to import any Materialx document as a material in queries. By default, the material is collapsed, and any exposed parameters are available to users. When it is in that state, the look is kept as reference so that any modifications to the actual Materialx document file gets propagated accordingly in queries. Next, please. At any time, users can expand Materialx looks to access to the node graph for editing. When expanded, looks are localized in the current scene, and the link to the reference is severed. However, once the edit is completed, the look can be collapsed and re-exported and relinked to reference the new Materialx document. Next, please. Since Materialx looks are transported in USDs, Materialx look dev assets are properly brought inside queries. This is huge since full assets can now be self-contained in a truly portable way. As we can see, we have the same asset in USD view and in queries. Next, please. When in queries, users can edit materials parameters through overrides applied on top of the USD reference. They can also go further by localizing the material for further editing. Of course, they can re-export the updated USD if they are willing to. Next, please. Obviously, this also means that fully look dev scenes can be exported to USD with their looks when they are look dev'd using Materialx nodes. Here, we have our fully look dev query scenes in USD view. That's really cool. And next, please. And that's it. Thank you.
Hi, my name is Emma Holthouser. I'm currently a rendering engineer intern at Lucasfilm. I'm going to be speaking about the Open Materialx graph editor. Next slide, please. So I wanted to start off with the motivation behind the project. It comes from requests both from artists at ILM as well as members of the Materialx community asking for a way to edit Materialx files without needing another software or program. So the goal of this project is to allow for an open source way to edit Materialx graphs. Next slide, please. So once we had this goal, we turned to the visuals for the project. So I just wanted to go over some of the dependencies that we're using. We're using ImGUI for our UI library, Node Editor for ImGUI for our Node library, and Materialx Render for rendering. Next slide, please. So now I'm going to go over some of the current features of the graph editor. So first off, you can load a Materialx file. So in this image, I've loaded the standard surface marble solid material, and this is what it looks like right off the bat. All of the nodes are laid out, and you can see how they're all connected. Next slide. So now if we want to add a node, we can do so by clicking Tab, which will pull up our Add Node window. And then we can add any nodes that we want to the node graph and update these existing graphs. Next slide. So if we don't have a Materialx file that we want to edit, we can also just start from scratch. So in this image, I've started by just adding a bunch of nodes to create my own material. And then once we have something that we like, we can go ahead and save it out as an MTLX file. Next slide. Another feature is the ability to connect nodes. So as long as there's a valid connection between the output and the input, you can connect those nodes with a link. Next slide. We also have the node property editor. So I currently have the bias node selected. So once you have the node selected, on the left-hand side of the graph editor, it will show all of that node's information. So we have the node's name, its category, and all of its inputs. So with this, we can edit the node's name as well as edit any parameters that the node has. Next slide. So speaking of editing parameters, doing so updates the current material, and we can see that through the interactive rendering feature of the graph editor. So in this example, I have scale noise selected. It's also part of the standard surface marble solid material. So with scale noise selected, if I change one of the inputs. I changed it to 11 here. That will change the fractal noise of the marble. And you can see that in the render view window to the left. Next slide. So those were some of the current features of the graph editor. I also wanted to touch on the future features. So one of those will be a thumbnail render in the property editor. So for the thumbnail render, it will showcase the rendered node graph up to the currently selected node. We're also going to have the hierarchical traversal of node graphs. So we'll be able to dive in to any node that has a subgraph. So an example of this would be node graph nodes, being able to dive into a node graph node, as well as a llama node or a translation graph. And all of these will be a part of the open source release that's planned for fall of 2022. Next slide. And thank you to everyone here for all of their contributions. Thank you.
Hello. So next slide, please. So the usual blurb. Next slide. So yeah, we love open source projects, and we always strive to be, good citizens in order to cater for, portable workflows for our customers. And there, Materialx is no exception. And it's something we really believe in. And it's also very important to us too that we contribute back to the community. So I'm going to go through some of the contributions we've had this year, over last year. So Materialx Web is something that was introduced last year, actually, by Sebastian Orr's team, and it was merged early this year. And also, we have started developing the Vulcan shader generator. So you can see it's still under development, so it still has limitations, but it's based on the GLSL shader gen, but it generates Vulcan compliant GLSL. And so we're planning to bring that to Materialx, so we're looking for any Vulcan experts to give us guidance there. Next slide, please. And we don't shy away from making any sort of contribution. So we've helped, for instance, to modernize CMake code generation, and we've been keeping USD, the repo up to date with the Materialx releases will come out. And that's very important for us because, next slide, please. Because for Materialx in Maya USD, because we currently support 1.384, and it supports all sorts of features, dome lights, and it can embed new code, color management nodes and utility nodes on demand when necessary. We can export my utility nodes and stuff, so you can see the chess set there in the viewport. Next slide, please. That is also very important. Maya USD comes in there as well. So we're currently working on lookdevx. It's our material graph editor. And its guiding light is basically a portable Materialx workflows. And it's designed to support different data models. So we can support Materialx and node graphs, that data model on its own. So, but we can also leverage using Materialx and Arnold node graphs encoded in USD, and it's also designed to support different DCCs and different renderers. It's also meant to be artist-friendly. It's got lots of fully featured graph management tools, publishing workflows, etc. As you can see, some of you may have seen screenshots from this before and thinking, okay, I've seen this, but and while there have been improvements in terms of the node graph editors, etc., the majority of the brunt of the work we've been doing lately is to leverage Maya USD to enable Maya USD material workflows, basically. And it will be available soon in the Maya Beta program, where we're focusing on, and where you'll get what you get is Materialx, Arnold, and other renderers through USD, using Maya USD workflows. So next slide, please. Additionally, we're working on an Autodesk material library. That's all Materialx using standard surface as the core material model. And it already has many hundreds of models. It's all calibrated HDR and real-world light as well. That's very exciting, and we'll let you know more later when we have more on that. So next slide, please. In terms of manufacturing materials, we ported all the legacy materials to standard surface, well, to Materialx with standard surface. As you can see, there's definitely an improvement in terms of rendering quality. As you can see, on the left, we have the legacy materials and the standard surface ported materials there. And so next slide, please. And also, that was done using the shaded translation graphs that the Ashwin and his team was contributing. Also another use case is to then use the shaded translation graphs to export it to different targets, where we can target USDZ for Apple AR, for instance, or GLTF for web viewing. And you can see there from the Inventor screen shot from there, and then you can see at the top you have GLTF and USDZ on the bottom. And this is something was also discussed last year, so there's a link to the slides there if you're interested. Next slide, please. So also in terms of Materialx in Arnold, so it's important to note as well, Materialx has been supported in Arnold since 2018 from Arnold 5.1. And we have all the API and tooling to exchange materials between DCCs, and that's what our customers have been doing in production, and it's been very successful. And it's also important to note that we support both the OSL code generation, so we can take any graph and generate it, but we also have sort of node definitions for Arnold, so you can use any, you can use any Arnold native node, Arnold shader in Materialx, and that's been heavily used by customers as well. Then a sneak peek, as you can see here, you can see the image on the right. We're working on the USD Materialx workflows, and it's compatible with MyUSD, lookdevx, Houdini Solaris, but it works both with the Hydra render delegate and the procedural. That's very important as well. And there's also, we introduced a new API to take any node reference, any definition, and you can ask for the OSL code for Arnold for that as well. And to end with, maybe I've gone a bit fast, but just going to end with the last thing I'm going to show you is this couple of slides were coming from Arnold of the chess set. So, next slide. Yeah. So that's beautiful, isn't it? Thank you very much. That's it for me. Thanks to everyone.
All right, I'm Brian Savery. I work for AMD on the, what's that?
You have to say next.
Oh, I don't have to say next, great, perfect. Okay, well, that'll make my slides like 5 seconds shorter. I work for AMD on the advanced rendering group. We've been working with the Materialx group for quite a while, and I'm gonna cover our material library that we published for Materialx and a couple other things. So at AMD, we're obviously a hardware vendor, but we're really focused on these open source technologies that allow usage between different hardware vendors and software. So really, we're trying to enable things, and our main website where you can find all these things is called gpopen.com. We actually posted a Materialx library, and I think it's, as right now, the only publicly available Materialx library other than the examples on GitHub. So there's 347 materials on there right now. It allows people to upload their own materials. Most of the materials on there are sort of this PBR map style materials, but there's some procedural ones as well. And really, we are putting this out there both as an example and for other software vendors to integrate into their software. So there's an API that's available if you join the Slack chat for Academy Software Foundation. There's an API that you could actually pull in the materials into your application and use them right there. And obviously, people can contribute materials there as well. Actually, if I go back, we're actually using Autodesk's web preview code for previewing the materials in your browser there. And then the swatches, we're all rendering with our own renderer, which is called AMD Prorender. We've had this AMD Prorender. It's, again, meant to be cross-platform, not locking you into one hardware vendor or sort of one software ecosystem. And we really believe that. That's why we call everything GPU open at AMD. The render actually works on Mac OS as well as Linux and Windows. It actually has a Vulcan backend as well as an OpenCL backend. Does CPU, GPU rendering as well as supports Materialx. So we're able to do all of the swatch rendering and obviously render that same chess scene that I'm sure you're all sick of seeing by now. So the render is closed source. It's not an open source renderer, but the licensing for it is all Apache 2 licensing, so it's very easy to integrate into different applications. You know, we have it delivered with SolidWorks Visualize. We have various plugins for the renderer, and like I said, most of these applications and the plugins are supporting Materialx as well. If the application that plugs into supports Materialx. So both having the library, we're able to push the materials into the plugins. So in this example, it's Blender that we're able to push these materials that are served in our library, upload them to Blender, render them inside Blender with the Prorender software. So traditionally, a lot of plugins for rendering have been the sort of standard, Maya Blender style rendering plugins, and we did that initially with Prorender as well. But recently, we've sort of shifted our focus onto this USD and Materialx workflow, and the benefits there are really great for the artists who are able to switch back and forth between renderers. Maybe they want to do their preview renders with something like Prorender, or they want to do their final renders with something like Arnold. And with Materialx and USD, they can kind of, get similar renders between the different renders, or maybe they have to go and deliver it to the web for something. And now we have a system with Materialx and USD where we can get those similar renders between the different renders. So, and the other thing we've noticed is, going from this model where we had this sort of like traditional rendering plugin to more of this this model where your rendering plugin is a Hydra delegate and something that supports Materialx. Each renderer doesn't have to write the same code. So, for example, if there's 5 different renderers that want to write plugins for Blender or Maya, they don't each one have to write some code that exports the Blender data to the renderer. They could just have their Hydra delegate and then be able to plug that into this Hydra interface and basically just plug and play there. And it's deduplicating a lot of code between different renderers. So we really believe in this workflow, and we're moving towards that as opposed to the standard rendering plugins. So I think the slide got cut off a little bit there, but this mode. So we've published a plugin for Blender already that supports Hydra rendering, and we can import Materialx materials and render those and be able to assemble the Materialx materials inside of Blender. So you've seen something similar with Houdini and Maya, but for the open source users here, if people are looking at Blender, we think it's really important to have that Hydra rendering option inside of Blender and be able to assemble your Materialx materials and do that all inside of Blender. So I have an example here of how the plugin's working. On the top is a USD composition node graph, and at the bottom we have the Materialx node graph. So it's pretty complex material there, but you're able to. And then on the left, you have the renderer running in the viewport there. So that's Hydra rendering in the Blender viewport. And we're using the Prorender backend for Hydra right now, the render delegate, but you can use the Storm delegate as well as RenderMan we support now, and we haven't tested, all the different Hydra delegates that are out there, but theoretically, any renderer that will support Materialx and Hydra, we should just be able to plug into this. So right now, it's an add-on for Blender that's open source. We're hoping actually to get this to more users and push this to the Blender source code, so this will be delivered to more users. Really, the big picture we're trying to promote here is that having this more USD Materialx based workflow for rendering, it's better for everyone. We have a lot more options here, and we can really try to make it easier both for the users to try out different renders and for renderers to integrate into these applications. As it seems like everyone's here is moving towards this workflow, and it's a good thing we're trying to promote it with some of the stuff that we're doing at AMD. So I think that's it for me. Like I said, gpopen.com. You can get the materials, and then also check out our rendering plugins and everything else there. And that's it.
I think I need to start on my slides.
All right. There we go. All right.
Okay, thank you. I'm Bernard Kwok. I'm representing Khronos and Materialx. Today I'll be giving an update on GLTF and Materialx on behalf of Pablo, Delgado, as well as other contributors in this area. In this session, I'll be covering how GLTF has been introduced to Materialx, as well as give an update on web support in general. Next slide. A major milestone for introducing GLTF to Materialx is adding in the GLTF PBR shading model. Initial and ongoing work is thanks to Tobias Hausler from Dassault. Complementary definitions such as shader translation and pattern graph nodes are in progress. So in order to ensure standardization, all of these definitions are composed of existing nodes found in the Materialx PBR and standard libraries. Next slide. From a user point of view, the shading model is represented as a single node, but under the covers, the logic is implemented as a Materialx graph published as a node definition. In addition to using the PBR nodes, requirements for this model are actually helping to drive implementation improvements. So for details on the PBR logic, please see this year's Khronos BOF presentation. Next slide, please. From an interface perspective, the new shader definition is treated like any other definition. So it can support capabilities such as versioning, metadata tagging, and usage in arbitrary node graphs. From a rendering perspective, any of the existing shader generators can be used to provide consistent shading. So on the right, you can see OpenGLES and MDL. Next slide, please. So this basic support gives users access to native workflows within Materialx. The two basic starting points are GLTF PBR for realistic rendering, or you can use unlit surface for false coloring. Beyond that, users should be aware that GLTF constraints are actually not explicitly formalized within Materialx, and there's a list there. Next slide, please. So work to allow remapping between shading models is being spearheaded by folks at Autodesk, as Ern mentioned. So that's namely Nicolas, Christian Robles, and Ashwin Bhatt. So the first goal is to allow conversion from standard surface to GLTF PBR. So the workflow is actually data-driven using shader translation and texture graphs for shader model conversion and texture baking. On the far right, you can see an example shown in the Dassault render. Next slide, please. For those working with USD, GLTF PBR and unlit definitions are both available via Materialx, starting with the 22.08 release. So while Materialx and USD interop is mostly established and reaching maturity, there's still a lot of ongoing discussion around the role and workflows for GLTF. Next slide, please. So for now, there's some basic interop supported via GLTF translators. So the most complete is the Kwok utility from Pablo Delgado. So this can translate from GLTF either directly or indirectly via Materialx onwards to USD. The desire is hopefully that there's a standardized graph that we can use for bidirectional data transfer. Next slide, please. So in order to ensure validity, there's been improvements for the Materialx testing framework. So for basic shader syntax validation, this is now complete with the addition of GL slang validator for OpenGL variants. So this complements using OSLC and MDLC for OSL and MDL respectively. For render testing, setting up reference path tracers for both web and desktop is work in progress. Next slide, please. So for the core Materialx distribution, we're hoping to get parity between the desktop and web viewers. So on the desktop side, the GLTF geometry import is now supported. And on the website, material editing and assignment support is there. For visualization, it's worth noting, as mentioned in the previous presentation, that AMD's material library also supports web previews and should also support GLTF PBR if you want to use that as your shading model. Next slide, please. So in summary, the GLTF shading model is now available for Materialx and USD. So standardizing and open sourcing the GLTF export workflow is something that's in progress. In order to support configurability and performance, we're looking at options in order to make the shading more real-time, as well as looking at how we can kind of reduce the resource overhead for things like stream requirements. More broadly, there's still discussion on how attribute and node graph characteristics found in authoring workflows could potentially make it through to transmission workflows. So for instance, could you actually have something like a node graph, for instance, in GLTF or 3.js? Next slide, please. So finally, a big thanks to all of these and other folks that were involved in the work presented. Thank you.
The background of how we support the current status, also how we support Materialx in Omniverse. So what's Omniverse? NVIDIA Omniverse enables workflows from top industry tools using real-time collaboration and open standards, such as USD for the scene representation, MDL for materials, or physics for the simulation. So coordinate that a little bit here. So let me show you two quick examples of RTX real-time renderings in Omniverse from the marbles scene using a diverse set of MDL materials. So as one of the foundations how we implement Materialx support, we use then internally the MDL, the material definition language. I want to highlight that this is open sourced since a couple of years now. SIGGRAPH 2018 was the open sourcing of the MDL SDK for that. It uses a BSD3 clause license for that. It's the full MDL SDK, including a core API and more things. And I want to also highlight here for the open source aspects that also the Omniverse core materials are open sourced, also with the BSD3 clause license. They ship with the different Omniverse applications. This includes the Omni PBR family of material definitions and also the Omni Surface family of material definitions there, and the core definitions which are used in the material graph editor in Omniverse. So this is a rich set of artist-friendly building blocks and components to build materials with the graph editor there. Now, having that as a foundation and as a target, we had a couple of years ago the project to support MDL as a backend for Materialx. That was jointly with Autodesk and Lucasfilm. These are basically the references here for Materialx, and we are talking here about the shader gen component that we used here, and we created then the Materialx Gen MDL backend. This is the library for MDL code generation in the Materialx repository. It had been released then officially as with Materialx 1.38 in the repository. It's open sourced on GitHub, as you know. At the time, we were able to render these things. Here on the left, you see iRay using MDL, Arnold, and the Materialx view, showing the same asset with the Materialx materials. We later got a bit more content here as well. We are showing this one. We showed this one here at the NVIDIA GTC conference spring this year. And with the integration in Omniverse here, you see the Create application. And so what's the current status? So how do we actually implement this thing? What's the foundation of that? It's based on the USD Materialx plugin that comes with the USD SDK. It has two different representations of Materialx nodes in the USD. One would be a reference with an asset path to Materialx file, and the other one is actually the flattened view with the whole shade graph broken down into individual USD shade nodes, all with individual info ID references to the tokens. We want to support both of those. So actually our implementation in Omniverse then imports, when importing a Materialx file, we recreate a Materialx document from the USD representation. That actually supports then both representation for us and uses then the Materialx Gen MDL backend to create a corresponding MDL file that's stored on disk. And the MDL material is then also referenced in USD because you can have multiple representations of different material models in USD shade representation here with a source type for MDL. So that's actually then a sidecar file that goes along with the Materialx and enables the rendering in USD with MDL capable renderers like the RTX real-time and path trace and iRay renderers in Omniverse. And we keep at the same time the Materialx materials in there intact, so they stay in the USD file, so other renderers can pick up the original Materialx representations as well. Now, there are still details in the workflow to be done. So of course, if we add this file, just on opening a USD file, we don't want to change that and basically have the additional sidecar file referenced in the USD node. So we're working on the workflows. It has to be, this addition has to be transitory until we start editing things. And also the integration in the material graph editor to make it multimodal for the different representations is still to be done. The availability for our products or the releases is something like the fourth quarter of 2022. Now, how do these results now look like with the chessboard scene here? It's the first screenshot for that one. That's an animation rendered out of that. The latest addition is actually the subsurface scattering that we are also fully implemented now with the MDL backend for Materialx. And that's the daylight screenshot for that one. So what are next steps for the Materialx Gen MDL backend that we want to work on? Right now it's a very complete open source reference implementation. So if you also include the MDL open source implementations for all the BSDFs, it's a rich resource of things that I invite you to make use of and look at how things are implemented there. What we want to do is we want to upgrade from the MDL 1.6 implementation that is used right now in the Gen MDL backend to MDL 1.7. That allows us to complete outstanding limitations because we have synchronized the specifications even further in these efforts. So we can do then full layering support for Sheen BSDF. We can do emissive volumes. We can do arbitrary weights on the add BSDF Materialx node and also non-uniform weights for the mix EDF node. And I already mentioned subsurface BSDF hadn't been fully implemented. It is now, and we are contributing it back to the repo as we speak somewhat these days. That concludes my presentation. I want to also highlight that we will talk on Thursday morning at 9 a.m. in the NVIDIA sponsored room. It's in the Conference Center West, room 121, and we'll talk about all other aspects of material workflows in Omniverse and a bit more there. I want to acknowledge the work that has been done just by Kai, Derek, Charles, Frankie, and Jan. Thanks a lot.
Hello everybody, I'm Adrian, and I'll be talking about the project we've been doing between OSL and Materialx to have a common set of closures. So I'm going to talk about why do we introduce a new set of closures. I'm going to then go over the closure and describe them. I'll show a Uber shader implementation sample with those set of closure, and then talk about next steps. So first, a bit of a word like what do we call a closure in the OSL world? So a closure is an object that has a type, parameters, optional parameters, and an RGB weight. That object is emitted in a shader and then passed to the renderer for integration, because OSL is not really a language in which you write integrators. It's a language where you write shaders and then pass those objects to the integrators, and the implementation is renderer specific. So the problem with the existing predefined set of closures in OSL is that not all of them are relevant. I think we still have a Guiard closure in them, and which haven't seen in the world for a long time. And therefore, that set of closure is kind of loosely implemented in OSL-enabled renderers. Like, not everybody supports everything. It's hard to have a full picture of what is supported. Now, on the other hand, Materialx, the Materialx project, has code generators. It generates OSL and GLSL. So the GLSL code kind of stands by itself. It does integration, the shader, and everything. But the OSL code relies on closures, because again, OSL is not meant to write integrators. So the OSL code generator should rely on a widely supported set of closures and fully featured to be able to represent most of the materials out there. So something that the Materialx and OSL developers worked on over the past year is a common set of closures that is capable of representing modern materials. And this is a very collaborative project. If you were to look at all the pull requests that are mentioned in that presentation, you'd see like a wide variety of authors. Many people contributed to the technical discussion for the design of closures. Many people contributed to the code. So we thank all the people who were involved in that project. And it's an ongoing project. So that new set of, let's talk about the project status. That new set of closure is now specified. The specification is not set in stone. It's still evolving as we speak. We still have like an ongoing discussion, for example, on volume closures. But it's specified and included in OSL as a header. And you can see a summary of the discussion if you were to look at the pull request links over there. And the current part of the project is that there's the ongoing work is to have to provide a reference implementation for all the closures in OSL test render. OSL test render is really the part of OSL that you want to look at if you want to integrate OSL in your renderer. So it kind of makes sense to have an implementation of those closures in there. So now we're going to look at all the closures that are supported, and for every closure there's a render using test render that's going to end up in the OSL test suite, showing kind of a wedge of a section of parameters for each closure. So we have the usual ORNIR diffuse, a second diffuse BSDF, which is the Burley diffuse BSDF. It has a diffuse Fresnel retroreflection. After that, we have a set of microfacet BSDFs, so dielectric BSDF, like really very, very classic parameterization with the IOR. Conductor BSDF, it has a slightly different Fresnel parameterization. It's meant to work with the so-called friendly conductor Fresnel parameterization, where you pass an extension and a reflection color. A differently parameterized dielectric BSDF using the Schlick curve. Translucent BSDF, which is basically like a retroreflective diffuse, or retrotransmissive diffuse, sorry. Transparency, like to implement transparency, that's fairly straightforward, no pun intended. Subsurface scattering BSSRDF. So this is one of the few where there's not real support to test render, because test render doesn't have a fully featured BSSRDF integrator. There's an ongoing discussion on how we could improve on that. So that image is really, those closures will compile in the test suite in OSL, but they will just default to diffuse. So the backscattering microfacet closure is a sheen. This is now fully implemented in test render. So closures represent BSDFs, BSSRDFs, but also emission functions. So really basically an emission closure. And volume closures as well. The volume closures in that context are going to be used for interior closures, basically to describe what happens when you're shading inside glass, for example. And again, there's no volumetric integrator in test render, so those images are rendered with Arnold, which has support for those closures. But yeah, there's an ongoing discussion on what we're going to do with test render regarding to volumetric integration. So I think, yeah, in test render, they're now implemented very recently as extension only. So we have an anisotropic volume distribution function and an homogeneous material one. This is a very interesting closure. So I told you, like, closures can represent BSDFs, BSRDFs, emission, and phase function. But really, those are arbitrary objects. You can have a closure to write to AOV. You can have a closure to do like printfs in the render. Those are really arbitrary objects that you pass on to the renderer, and the renderer can do whatever it wants with it. One thing that is very important in modern Uber shader is the layering and the layering model, and more on that later. So in the specification, we introduced the layer closure, and it's really meant to represent a vertical layer of BSDF. So you have a top BSDF, a base BSDF, or a BSSRDF even, and you delay the decision on how you're going to mix those two closures to the integrator. So the integrator could do something as simple as compute the reflectance of the top closure, then pass the rest of the energy to the base closure, or do a full brute force Monte Carlo simulation to compute the thickness between the two, the thickness of the material, for example. So that's really a way of offloading the decision to the place where it can be more efficiently computed. And here you have an example of dielectric microfacet and retroreflection being layered on top of diffuse. And this is supported in test render. So speaking of layered materials, so this is a very now common layer model. This is the Autodesk standard surface layering model. And this is a render of that same model using the standard Materialx closures in OSL in test render. So very classic model with coating, a mix of specular reflection, transmission, emission, metalness, something that most of you, I'm guessing, are very familiar with. This can be represented using a somewhat complex, but not too complex parameterization. Like those are all the parameters in the standard surface specification. And the nice thing about that new set of closure is that it is very easy to represent that somewhat complex layering model with them. So if you look at this, so this is literally the code, and that's really the code that was used to generate this image to implement the standard surface layering model. So it's, if you were to look closely at the code, it's a mix of mix and layer closures, implementing the various components of the shader. This is really now compiling and rendering in a cell test render. So what comes next? We really want to iron out the implementation in test render, make sure that all the hard surface closures at least are well defined and agreed on. Like while rendering those images, I noticed a few bugs, so there's probably like a tiny bit more work there, but we're nearly there. There's an ongoing discussion about whether we want to expand the capabilities of test render to implement SSS closures and volume closure. Like test render needs to be simple, so that people can read it and figure out how to implement an OSL renderer. So maybe a full integrator is not on the plan yet, but we could go with simple approximation or something like that. But that's an ongoing discussion. So the very, very important thing that needs to happen now is that render writers should implement that new set of closures in their renderer. And I know it's something that everybody, including us in Arnold, are looking at. And this is important because what comes next? What comes next is that the Materialx OSL generator is going to start emitting those closures. And it's a pull request that is in progress right now. All right. Thank you.
I'm really excited about that work because it's been a thorn in our side for a really long time. OSL dates from a time that we weren't really sure what the right set of closures ought to be. We proposed some early in the spec. Even at Imageworks in our renderer, we went through many cycles of changing our minds about what the canonical set was that we like to use in production. And OSL didn't even really keep up with that in terms of the public spec. And so, and for many years we kept saying, like, is it really baked in our minds? Do we know what we should do and tell the rest of the world to do? Do we have that confidence? And when we realized that things had really settled down in Materialx and that looked like the right set of canonical BSDFs to support, this collaboration is something that I think fills that gap that has been embarrassing for a long time for us in OSL land. Great. So just in case anyone is behind the times here, and by the way, I'm winging this because when I wrote this up, there were speaker notes, and I don't see the speaker notes, but bear with me. OSL is the de facto standard for production path tracing these days. It's delivered as an open source project that consists of both the language spec as well as libraries that you use in a renderer to implement the heart of it. There's a pretty wide range of both commercial and studio proprietary renderers, as well as open source projects that support it these days. So it's pretty widely out there. It started, of course, at Sony Imageworks, was open source pretty early on in its history, and has been an ASWF, has been its home for the last few years. So I want to give just a really brief update on what's up with the project over the past year. We haven't been in front of people for a long time, so this is nice. Releases, we've been a little bit behind the times on this. A lot of the studios that use it heavily and a lot of the products kind of work out of master pretty close to the tip. And so we'd fallen a little bit behind on making, stable API official tag releases. And we apologize for that, but we have one now, and one of the big missing pieces is we wanted to get this new BSDF standardization in it. So now I've lied ever so slightly because when I made this slide, I really thought that I would have the tag in there by the time I was standing in front of you, and I don't, but I promise it'll be this week. But a branch for what we're calling 1.12 is truly imminent, and that will kind of put it into beta, and hopefully September 1st-ish or as soon thereafter as we can. We'll call that a stable release, and we continue to update it, but that just means that we promise not to break the APIs for a while. But like I said, a lot of us have been using OSL, pretty much straight out of the main branch. So this isn't untested, this isn't not production proven. Most of the movies you see out there have probably been using exactly this code. So in terms of the major new things that are in this release, of course the support for the closures in test render and in the spec is a big part of what is new. And there are two other kind of big technological shifts, both of which have been worked on for some time, but I think this is the first real official release when we sort of say okay, it's kind of ready for prime time. So one of them is batch shading mode. So just as a review, the traditional way that OSL has worked is it JITs machine code to be operated, but the gist of that is you're invoking it on one point at a time. So imagine you're tracing a ray, you hit something, and then you shade the endpoint of that ray. So the gist of this work, which was implemented primarily by Intel and Pixar, is to shade in batches. So instead of one point at a time, you're collecting typically 8, you're trying to fill either 8 or 16 point batch. of points that you need to shade that have the same material. And it's exploiting the Intel, primarily AVX 512, but also AVX2 instruction sets, which have SIMD operations where, like, if you're, just as an example, if you're adding 8 numbers and another 8 numbers pairwise, that can be done in one instruction. Sort of assuming that the numbers are all laid out so that they're always in the right adjacent memory locations. And so anytime you're on all these modern chips, if you're just adding 2 numbers, like, you're wasting most of the computation that you have available to you. And so the gist of this is that it's trying to sort of keep those floating point units running flat out to the greatest extent possible. And this is as far as I understand, like, it's already in use in PR man. So it's it's working and everything. And we basically, part of this release is, like, that work, which has been going on for a long time, is pretty much settled down and stable and, like, fully feature complete. The other big technological area that we've been working on a lot lately is a GPU-based backend. In this particular context, we mean CUDA and optics-based. And this is work that was done sort of jointly by people from NVIDIA, people from Sony, and some others here and there. And this is primarily for optics-based renderers that run on NVIDIA GPUs. And it's mostly working. I wouldn't call it feature complete. There are areas of the language that are not quite there. We still have some work to do. That will be ongoing work over the course of the next release cycle. But it works to a pretty good extent, and several renderers are getting a lot of use out of it already. So a big part of the roadmap for the next release is going to be to fully flesh this out. And I want to show a little demo. This came from Pixar. It's just showing some interactive sort of look dev, just to give an idea of, like, these modes. Just it brings a level of interactivity that we sort of always wanted to shader execution. So nice fast updates on things. And I'll move on because I do want to leave time for Q&A for everybody. So in terms of roadmap for OSL over the next year, which will be another big release cycle with us, and these are just sort of the biggest hit items that we've been talking about in the OSL TSC. So one is, of course, we want to take the optics backend and really finish those last pesky bits and bring it up to sort of full, or as close as possible to a meaningful full feature parity with everything that it could previously have done on the CPUs. As a little bit of like super geeky technical stuff, if you've been hanging out in the OSL TSC, there's an underneath shift in how a lot of the functionality that's currently left up to the renderer is going from one kind of callbacks back into this renderer services object the renderer controls into a more integrated sort of renderer provides some LOVM code that will like sort of fully turn it into JITted code, and that's nice both for performance issues on the CPU, but also it unlocks some of that functionality on the GPU where some of those unimplemented things are unimplemented because we hadn't quite wrapped our minds around what to do with those bits that currently aren't really implemented in OSL. They kind of rely on the renderer to supply those parts. There are some types that, some data types that Materialx and other people have used for a while. Basically, 2-element vectors and 4-element vectors and relatives of that were never quite supported in OSL. That was actually part of the design to not support those, but now we live in an ecosystem where people expect them. And so the current way of in OSL to do that is defining structs and stuff, but the lack of those as a core supported fundamental data type is starting to show its age. So we're going to go and implement those as real first-class objects. There's something that we've been talking about for a long time, about adding a certain kind of flexibility where the shader networks, instead of the data like always flowing in one direction, there's a way to sort of reevaluate earlier parts of the shader graph with certain parameters reevaluated. And that leads, it's a little scary, but it leads to a lot of really interesting flexibility and new kinds of expressiveness in the way the shaders are able to function. And then the last thing that is a big thing I'd like to get tackled is additional backends. Like, we'd love to have the ability to sort of easily extend to like emit HLSL on the backside and other things like that. And that requires a bit of infrastructure to do. Now, that's a big list of big ticket items, and frankly, in the current environment, that's going to be a really tall order to tackle all of those things. So here's my plea to people who are interested in OSL, are dependent on it. This is, I know it looks from the outside sometimes like this just smoothly chugs along and you don't need to do anything, but in fact, it's like it's the swan that looks graceful above the water, but under the water, the little legs are going super fast and it's wearing itself out. And so all sorts of help is greatly appreciated, and we could use more hands on this project if this is the kind of thing that is interesting to you. And it's not all about coding the deep, dark internals. There are always things that can be done, even to newcomers of the project. Even if it's things that are just offloading certain work from the core developers, that is helpful too. So our usual communication methods, we have a mail list that anyone can sign up for. Every other week we have a Zoom call for the technical steering committee. Those are open to everybody. We discuss all sorts of interesting things there, not just core OSL issues, but also it's a place where shader leads from different companies are all talking about the sort of common issues that they all face, not even just in OSL. And so some pretty interesting stuff goes on there. And of course, there's an open shading language Slack channel on the ASWF Slack. So hope to see more of you on any of those places. And that's it. So I think not just for me, but for any of the speakers, I think this is our chance for Q&A discussion. Anything else?
Any questions?
Stunned silence only.
We do have some, sorry, just checking my audio. We do have some questions in the Zoom chat. If we can resolve the audio. Hello. Yeah, so we had a bunch of questions. I guess first, I just want to thank all the speakers that presented today. This is some truly stunning work. And this is, again, a testament to the power of our operating under the Academy Software Foundation. There's no way that we could have achieved this degree of velocity and integration just with Lucasfilm managing the entire project. So thanks to everyone, and thanks to the ASWF for their support. We had a bunch of virtual questions. Some of them have already been answered, but I can bring up some of the ones that have not yet been. We had Anders asking, is lookdevx open source? So that would be a question for Ern if he's around.
So lookdevx is not open source. That was quick, nice and easy.
Thank you, Ern. And then there's another question also from Anders. Is the graph editor planned to support Hydra for rendering? This is actually, sorry, this is not for Ern. This is about the open source editor. So this would be for Emma Holthouser. Emma, did you want to take that?
I was gonna say there's not plans for it right now at the current time, but if Jonathan wants to go ahead and mention if he had any thoughts about that as well.
Yeah, that's exactly right, Emma. There aren't yet plans, but it's going to be an open source project, and we've we've aimed with Emma's leadership on the project to make it as simple as possible and as easy to extend as possible. And the idea of extending it to become a hybrid delegate seems like a natural project that someone in the community could take on. There was one earlier question. Sorry about the audio, everyone. This is a question for Brian Savery relating to the license and the closed source versus open source nature of Prorender.
Yeah, is that the license of the materials or the Prorender stuff?
It's the Prorender renderer itself.
Okay. So Prorender itself is closed source. All of the plugins are open source, but the core renderer and the DLLs with that are closed source. So they have, I think it's Apache 2 license. Basically, it's permissive to use it. There's no restrictions on that. If you have any questions, like I said, just reach out to me either on Slack or there's contacts on gpopen.com. And in terms of licenses, I should also mention, I think I had it in my slides, but all the materials are permissively licensed. I think most of them are CC licensed, so you might have to attribute the original author of the materials, but there's no like restricted license on the materials as well.
Thanks so much, Brian.
Okay, great. Let's give it another round of applause for all of our speakers.